we're going to expand our discussion of limits to include something called L'Hopital's rule. I like to call it goodbye squeeze theorem. L'Hopital's rule is going to let us be able to find limits such as this. The limit as x approaches 0 of sine x over x, and we were going to find that that equals 1. L'Hopital's rule states that if I have f and g, and they're both differentiable on an open interval I, and that interval I contains a point a, and g prime of x is not equal to 0 on that whole interval I, as long as x does not equal a, then I can say the following. If both the limit as x approaches a of f of x and the limit of g of x as x approaches a is equal to 0, then I can do the following. I can say the limit as x approaches a of f of x divided by g of x is equal to the limit as x approaches a of the derivatives of f and g, that is f prime of x divided by g of x. This works as long as the limit on the right-hand side exists. I can let x approach infinity, negative infinity, a from the left-hand side and a from the right-hand side. There is a proof, but I'm not going to go through it. I'm just going to go ahead and start using some examples. If I take the limit as x approaches 1 of x cubed plus x squared minus 2x divided by x minus 1, if I go ahead and substitute x is equal to 1, I end up with 0 divided by 0. I've already explained that this is a form I can use L'Hopital's rule in, and I'm going to use the phrase indeterminate form. So if I have something in the form 0 over 0, this is considered indeterminate. That means I can use L'Hopital's rule. Let's go ahead and do that. Let's find the derivative of my numerator and the derivative of my denominator. Now I'll go ahead and substitute x equals 1. When I do that, I find that this limit is equal to 3. I always like confirming this with a graph, and sure enough, if I graph x cubed plus x squared minus 2x divided by x minus 1, I get this graph. If I use Desmos and hover over the point at x equals 1, it says it's undefined, but as we've already talked about limits, the limits are what the value approaches from the left-hand side and the right-hand side, and in this case it clearly equals 3. Let's do another example. Let's take the limit as x approaches 0 of square root of 9 plus 3x minus 3 divided by x. Again, if I do a direct substitution, I end up with 0 divided by 0, which is an indeterminate form. When I take the derivative of square root of 9 plus 3x, I'm going to have to remember to use the chain rule. That's where the 3 comes from. And then I get a 0 for the derivative of 3 with respect to x and a 1 in the denominator. So now when I substitute, I end up with 1/2. Sometimes we'll come into a situation where we'll have to use L'Hopital's rule twice. Let's look at two examples like that. If I take the limit as x approaches 0 of e to the x minus 1 divided by x squared, if I do direct substitution, I again get 0 divided by 0, which is indeterminate form. So let's use L'Hopital's. When I do this, however, I get again 0 over 0. So since this is still an indeterminate form, I can use L'Hopital's rule a second time. When I do that, I get it down to the limit as x approaches 0 of e to the x divided by 2. When I substitute in x equals 0, I get e to the 0 over 2, which is 1 over 2, or 1/2. Let's look at a second example. If I have the limit as x approaches 2 of x cubed minus 3x squared plus 4, all divided by x to the 4th minus 4x cubed plus 7x squared minus 12x plus 12, when I directly substitute x equals 2 into this, I end up with again 0 over 0 indeterminate form. Let's use L'Hopital's. And I again end up with a 0 divided by 0 indeterminate form. So I'll do this one more time. When I take the derivative again and plug in x equals 2, now I get 3 over 7. So L'Hopital's rule works great when I have something in the form 0 divided by 0. Notice indeterminate form we've defined as 0 over 0. It means 3 over 0 we could not use L'Hopital's rule for. 0 over 3, well, to be honest, you wouldn't bother with 0 over 3 because 0 over 3 is a valid number, that's just 0. But L'Hopital's rule does not work if I have infinity over 0. There are different forms of indeterminate form, however, than just 0 over 0, and that is when I have infinity over infinity. Let's look at some examples of this. Before I do an example, however, let me write explicitly our new L'Hopital's rule. I've simply added this bit. That is, if the limit of f of x as x approaches a is plus or minus infinity, and the limit as x approaches a of g of x is also plus or minus infinity, in addition to when they're both equal to 0, I can also use L'Hopital's rule. If I have the limit as x approaches infinity of 4x cubed minus 6x squared plus 1 divided by 2x cubed minus 10x plus 3, I find that this is infinity over infinity, which again is a indeterminate form. 0 over 0 and infinity over infinity. Remember, 0 over infinity is not indeterminate form. I think I'm going to have to take L'Hopital's rule and use it several times. Specifically 3 times, before I finally get to the form of this equaling 2. Let's do another example. When I do direct substitution of the limit of x approaches 0 from the positive side of natural log of x over cosecant x, I get negative infinity over infinity. Notice that this is fine. As long as it's infinity over infinity, if it's a negative or positive, we can still use L'Hopital's rule. After I take the derivatives, I'm going to have to do one more step. I'm going to have to simplify this. And when I simplify this and use my trigonometric relationships that cosecant of x is 1 over sine x and cotangent x is cosine x over sine x, I get this down to the following. And I end up with this being 0 over 0. So this is a different indeterminate form, but I can still use L'Hopital's rule. When I take the derivative, I use the chain rule and product rule to get this. And now when I substitute x is equal to 0 from the right-hand side, I get negative 0 over 1, which is just equal to 0. When I use L'Hopital's rule, I have to use it sometimes multiple times, and sometimes I'll go from indeterminate form of infinity over infinity to 0 over 0, but I can still use L'Hopital's rule in both of those situations. We need to consider what happens when L'Hopital's rule doesn't work. That is, at least it doesn't work directly. If I have 0 times infinity, if I have infinity minus infinity, 1 to the infinity, 0 to the 0, or infinity to the 0. These are situations where I can't directly use L'Hopital's rule. Let's take the first. When we have a situation where we end up with 0 times infinity. For example, if I have the limit as x approaches infinity of x squared times sine of 1 over 4x squared, that works out to be infinity times sine of 0, which is infinity times 0, if I do direct substitution. So what I'm going to do is rewrite this in a way that it can be represented by 0 divided by 0. If I rewrite this as the limit as x approaches infinity of sine 1 over 4x squared divided by 1 over x squared. 1 over x squared is the same thing as x squared. Once I've rewritten it in this form, I see that that actually equals 0 over 0. So now I can use L'Hopital's rule. Once I take the derivative using the chain rule, I see that I get down to this, and then I can simplify this even further to this, and when I let x approach infinity, this becomes 1/4. So in order to handle problems in the form of 0 times infinity, I need to recast it in terms of 0 over 0 or infinity over infinity. Now let's talk about using L'Hopital's rule when we have infinity minus infinity. It is so tempting to say that that just equals 0, but it doesn't. Infinity isn't a number like 6 or 6,356,000. Infinity can't be subtracted from itself. So in order to do this, we're going to change variables. That is, instead of having a limit as x goes to infinity of f of x, I'm going to change that x to t, and I'm going to let t approach 0 from the positive side. And I'm now going to think of this as f of 1 over t. 1 over 0 and infinity, those are equivalent. So let's see how this would work in an example. So if I had this example, if I let x just equal infinity, I'd get infinity minus infinity. I'd be tempted to call this 0, but it is not equal to 0. So let's rewrite this. The first thing I'm going to want to do is make this from a subtraction problem into multiplication. And I'm going to do that by factoring out an x. It's easy to see how x comes out of our first term, but the second term takes a little bit of manipulation. If I do this as my first step, recognizing that the square root of x squared is simply x, then I can factor this a little more easily. Now I'm in the form infinity times 0 again, so I'm going to use a technique I just learned and rewrite that x as 1 over x. So, although I could take the form I have now and do the first derivative of the numerator and denominator to use L'Hopital's rule. It's actually easier to replace x with t, letting t equal 0, as long as I replace 1 over x with t in each case. So now instead of x going to infinity, I can talk about t going to 0. And I'm going to have t approaching 0 from the positive side. When I do that, now it's much easier to use L'Hopital and take the derivatives. And when I do that, using the chain rule, I see that when I let t go to 0, that this whole thing ends up being 3 halves, which is much, much different than the 0 that we might have assumed with infinity minus infinity. Finally, if we have something such that the limit as x approaches a of f of x raised to the g of x power, if it equals 1 to the infinity, or 0 to the 0, or infinity to the 0 power, these are the steps we're going to take. We're first going to analyze that limit, and we're going to see if that ends up being 0 over 0 or infinity over infinity. If it does, we're going to use L'Hopital's rule like we've done in the past. Then we need to look at what L is. L is equal to that limit of, again, g of x, what was in the exponent, times the natural log of f of x. If L is finite, then the limit of x approaching a of f of x to the g of x is simply e to the L power. If L is infinite, then the limit we're looking for is also infinite. If L is equal to negative infinity, then the limit goes to 0. Let's look at 2 examples. If I look at the limit as x approaches 0 from the positive side of x to the x power, that leads to 0 to the 0 power. So let's go ahead and analyze the limit as x approaches a of g of x times the natural log of f of x. So the limit as x approaches 0 from the positive side of g of x times natural log of f of x is x times ln of x. If I plugged in 0, I would get 0 times infinity, so I know I need to rewrite this using the technique I just came up with. So I rewrite this as the natural log of x over 1 over x. Now when I use L'Hopital's rule, I get 1 over x divided by negative 1 over x squared. When I simplify that and substitute, I find that this limit is equal to 0. So we're not going to stop there. That's my L. So step 1 was to analyze using the 0 over 0, using L'Hopital's if necessary. Once I find my L, then I know the limit is, in the case of L being finite, which 0 is a very nice finite number, I need to plug that into e to the L, which is e to the 0 or 1. Let's look at a second example. If I use the example the limit as x approaches infinity of 1 plus 1 over x to the x power. If I do direct substitution, I get this as 1 to the infinite power. So I'm going to calculate L as before. So using similar techniques, using L'Hopital's rule and simplifying, I find that this limit is equal to 1. And when I plug that into my e to the L, I get e to the first power, or e. So the limit as x approaches infinity of 1 plus 1 over x to the x power is equal to e.